to the YouTube. So we're picking up in lecture 2 then. So this afternoon I wanted to go over the inclusion of time-varying predictors using one particular approach so that we could get very well acquainted with what exactly the effects in the model mean. Then tomorrow transition into multivariate versions of the same models and how the interpretations change when setting up the models one way versus another way, because that can be very confusing. So I will say at the outset that this is by far the #1 mistake that people make in fitting multi-level models. This problem of not fitting level 1 predictors accurately is rampant. I've seen a lot of well-intentioned tutorials that make the same mistake. It's made in some of the best-selling textbooks, not mine, of course. But if you take nothing else out of this workshop, I really hope to give you this message of how to properly model time-varying predictors. And the short answer is the same issues that you have to worry about in doing a multi-level model on the outcome side, you have to worry about on the predictor side too. There's no difference between X and Y in terms of how you have to think about piles of variance, and so that's the part where people get confused. So we'll talk first about transitioning out of growth curve type models like we had in the previous example and transitioning into within-person fluctuation models, and then returning back to the previous example tomorrow to try and put the two together. So these are studies then that I'm talking about today where time isn't really the issue. It's where you're just sampling people repeatedly to get a lot of data to look at within-person processes. So whether or not you had systematic effects of time or not, once they're included in the model, what we're really talking about is modeling what's left, the residuals. So time is no longer part of the story. It doesn't matter if it's time 1 or time 2, because if there's any effects of time, you've already put them in the model, whatever fixed effects you need, whatever random effects you need. So we're really just focusing on modeling the within-person fluctuation either around the trajectories or just around the means. And the reason that this topic is so complicated is that almost always effects of time-varying predictors are going to be at least 2 things. To the extent that time-varying predictors have between-person variance, they can show a between-person effect. And to the extent that they also have within-person variance, they can show a within-person effect. So for example, if we think about something like stress. So if I give you a study in which you're filling out daily diaries or something, and I ask you about stressful events, we would find that some days are worse than others, right? Some days are more stressful than others for all of us. So to the extent that we've observed people over time, and people are actually telling us different things each day, we have within-person variation of stress. But it also may be the case that some people are just more stressed out than others, period. There may be systematic person differences in reported levels of stress. And so to the extent that we have those, we have really a separate variable that belongs in the model that represents person variance as well as time-specific variance. And there's an easy way to quantify the extent to which you need to worry about representing its variance at multiple levels, and that's with our friend the intra-class correlation. So the 2 predictors that we have looked at so far are a special case of this. We had attitudes, which was time invariant. That would have had an intra-class correlation of 1, all between, all time invariant, all level 2. Age, on the other hand, would have an intra-class correlation in this design because everybody started at about the same age of 0, all within, all level 1. So we didn't have to worry about this, even though time is a time-varying predictor, because our version of time was purely level 1 within. That meant the only possible effect it could have is purely level 1 within. Likewise, the effect of attitudes, it's only level 2 variance in the first place, so we could only have a level 2 between effect in the first place. Class correlation greater than 0, it has at least some between level 2 variance, and that level 2 variance needs its own effect. To the extent that the intra-class correlation is less than 1, it has some within variance, and that within variance needs its own effect too. So So these effects may be in the same direction. For instance, if you think about the relationships between stress and health, people who have more stress than other people may feel worse, may have worse health than other people between persons. But it may be the case that when you are more stressed than usual, your health is worse than usual. So in that case, stress is bad for you, both between persons and within persons. Or you may also have instances in which the effects are in different directions because really the variables mean different things. So if I look at the link between exercise and blood pressure, between persons, people who exercise more often tend to have lower blood pressure than other people because blood pressure is a marker of physical health. But within persons, when you're actually moving during exercise, your blood pressure is higher than when you're at rest. So then it's a different kind of variable, and it has a different effect. So for the reason of differential meaning, we can have different levels have different effects. And also for scale, simply for the reasons of scale. All of these effects that we're looking at are unstandardized regression effects. That means they depend on what the standard deviation of x is and the standard deviation of y. So unless you have a pair of an outcome and a predictor that have the exact same intra-class correlation, that's the only way they would have the same amount of variance between as within. To the extent that they have different intra-class correlations, their predictors are on different scales than the outcome, and so you will end up with different effects at level 2 than level 1 simply because these effects are unstandardized. So there's 3 potential effects that we're going to be talking about here, main effects I should say. The first 2 are the easy one, and the one that's grayed out I want to get to later. But first, to the extent that a predictor that varies over time has between-person variance in it, does that between-person variance matter? So do people who tend to be higher in my X predictor tend to have a higher Y? If so, then I'd have a level 2 between effect, and that should capture random intercept variance, the same as any other kind of time invariant predictor. At level 1, if I'm higher than usual, then my own person mean, is my Y at that occasion higher than usual too? If so, then that predictor should account for residual variance at level 1. So I want to show you some pictures of what these types of effects would look like graphically. Actually, no, I want to do this first. That's coming next. So how we model time-varying predictors then. At level 2, what we're going to do is approximate between-person differences by computing the person's mean over time. And this person mean should be centered at a constant so that 0 is meaningful, just like any other predictor. The big question and where the confusion lies is what to do at level 1. And in longitudinal data, I have a clear favorite, and that is to use what is known as group mean centering in the clustered data literature, or person mean centering, in which we are centering at a variable. In longitudinal data, this makes more sense almost always. The other option is to not center at a variable and just to center at a constant, or not center at all, which is known as grand mean centering. But really the difference is that you're centering at a constant versus a variable. This approach makes more sense in clustered data, but is the one that is the easiest to screw up. When people screw this up, it's almost always because they're using grand mean centering inappropriately. And the tricky part about this is that even though the level 1 predictor has 2 choices in how you make it, its effect will end up being the same. It's the level 2 predictor's effect that switches depending on which you pick at level 1. So it takes practice to get used to thinking about how setting up the model changes what the model tells you. So here's what we're going to do first. My preferred method by far, because it is the easiest to get right. You carve up the time-varying predictor into the piles of variance that it should have. At level 2, we have a variable creating that I'm calling person mean x, and that's the person's mean minus a constant. So if I pick, say, the sample mean for the constant, then having a positive value of PMX means I have more of it than other people on average. Having a negative value means I have less of it, but the reference point is than other people. So people who is the way you would talk about effects of these kinds of predictors. At level 1, then, we are taking all of the person mean variance out by subtracting it from the original time-varying predictor. So the original time-varying x here minus the person's mean becomes this new within-person x predictor that we stick in the model instead. And it is purely level 1. So when within-person x is 0, you are at your own mean. So when it's positive, you have more of x than your own usual level. When it's negative, you have less, but it's relative to your usual. And this makes sense because what usual is up here in level 2. So we can talk about the effects of having more x than other people, as carried by the green, and more x than usual, as carried by the purple. And now we have equations and pictures. So this is what a model would look like then, including those two new predictors. So the original time-varying predictor is gone. It has been replaced by these two new versions that directly represent its variance at each level. So I don't have time or anything in this story because there's no effects of time and fluctuation data in a lot of cases, but you would have effects of time if you needed them. But to simplify here, I now have beta 1 as how each person gets their own effect potentially of within person x, where within person of x is defined as such. Level 2 then is person mean x, where it's defined as such. So then this fixed effect right here is the within person effect. It's the level 1 within person effect of having more x than usual. This one over here is the level 2 between effect of having more x than other people. And these two new predictors that we've created are orthogonal. They are uncorrelated with each other. Each has only its variance at its own level. And therefore, all it can possibly mean when you put it in a model is the effect at that level. So within person x has only level 1 variance, therefore it can only have a level 1 effect. Person mean x only has level 2 variance, therefore it can only have a level 2 effect. So it is pretty hard to screw this up in terms of interpretation. Each is clearly delineated in terms of what it's for. And I have here in parentheses an idea that you might have a random slope potentially too. So random slopes mean each person needs their own, right? In this context, it's not time, but they could get their own effect of within person x. So if this is the link between, say, stress and health, the extent to which feeling more stress makes you feel worse than usual could vary over people. People may differ in their reactivity or their resiliency. So we're cutting up the x then into our parts in the same way that we let the model do it for y. So this picture here displays graphically what we're thinking about in terms of piles of variance. We carve up my multi-level x into its level 2 person variance and its level 1 time variance, and we let each observed variable predict the corresponding variance pile on the y side, where the level 2 random intercept variance is approximated by the level 2 person mean variance on x. Likewise, the level 1 residual variance in y is approximated by this level 1 within person deviation on x. So this picture then may beg the question, well, why is one side boxes and the other side is circles? Why does the model get to form the variances on the y side, but we're making them ourselves on the x side? This idea that we could let the model make the variances for us on the x side too is the basis of multivariate multi-level modeling, or what some folks call multi-level SEM, and that's what we're getting to probably tomorrow. I don't think we're going to get there today. So these are the pictures that I had wanted to put in here. So these are demonstrations of what it would look like if we had between effects, within effects, both. So this picture then on the x-axis is time-varying stress. It's not time. Time is irrelevant right at this point. And severity, let's call this our favorite bad health outcome on y. And each person here is a different color. So I have a blue person, red, and green, and the yellow line through the person means is the between person effect. So in this picture, that yellow line has a slope of 1. For every 1 unit difference in mean stress, mean severity goes up by 1. The slope of the individual lines is the within-person effect, and in this picture, that slope is 0. So if this were your results, you would be very, very sad, because it meant you wasted your time doing a longitudinal study. All of the effect is cross-sectional. People who have more stress have worse health, the end. It's not, according to this picture, that if you have more stress than usual, you feel worse than usual. Within persons, there's no slope. You could have the opposite on the next slide. So, camera 1, camera 2, camera 1, camera 2. Now, if this were your result, now you've got something to talk about, because this shows the opposite pattern. The slope through the person means here, the between-person effect, is 0. It's not that people who are more stressed out feel worse. It's that when you are more stressed than usual, you feel worse than usual. So it's a purely within-person effect with no between effect. You could have some of each. So you could have positive effects, for instance, that vary in their magnitudes, a stronger between than within, but both. So what people do instead is fit one effect without differentiating the piles of variance and stick that slope in, and it ends up being a weighted combination of these different slopes more heavily weighted towards the within effect, and that pattern of inappropriate model specification is what I call smushing, when the level 1 and the level 2 effects are smushed together. That's the most common error, is to not differentiate these two things. To make it even more fun, we could have interactions among the two parts of the same variable. So here what I've added is person mean x as a predictor of the within-person effect. So this would say the effect of having more stress than usual in part depends on how much stress you have absolutely. And so person mean x could explain part of the reasons why people need their own effects of more stress than usual. The idea that people would still need their own effects after controlling for person mean x would be carried by this u1. So that type of interaction might create a picture that looks like this, where here we have a simple slope between that has a coefficient of 2, a simple slope within, which would be for the green line, that has a coefficient of 1, and a negative interaction term, such that for every additional unit of person mean stress, the within person slope becomes less positive by 0.5. So you have stronger effects of more stress than usual if you don't have a whole lot of stress to begin with. And up here, if you're all the way stressed out, having even more doesn't really faze you. I think of this as the difference between, say, like undergrads and maybe tenure track professors, something like that. When you don't have a lot of problems, the problems seem very big, until you get older and you realize what problems are, and then nothing fazes you, right? It's like, yeah, what's one more? Bring it on. So we can have a lot of different possibilities of how the between and within person information can relate to each other. So let's see how this would work in software. So I've got an example for you. This is fake data, once again inspired by real data. So the real data that inspired it are described in this publication. This is based on a daily diary study of 21 days of type 2 diabetics, and they were looking at more glucose the next day. So more is worse in terms of not having well-controlled diabetes. So the data are set up so the next day's glucose is on the same line as the current day's mood, which is going to be our time-varying predictor. And we're also going to be examining gender differences in the extent to which negative mood relates to glucose between and within persons. So because this is still a univariate multi-level model, we have only one outcome for which we are trying to find random intercepts and residual variances. we can fit these models within the mixed programs from before, and we can also fit them in M+. So I'll start with these because these are easier to build from, and then we'll look at how it would look in M+. So I have, in the data set already, I had created a person mean variable across the rows for each person. And this negative mood variable is actually a type of factor score such that the mean was already 0. So I'm putting it as -0 here just to remind you that you would want to center to make 0 mean something. So this is PMNM0 means person mean, negative mood, centered at 0. So this is going to be my level 2 predictor. My level 1 predictor within person negative mood is my original negative mood time varying column minus my person mean negative mood column. So I'm centering at a variable. And it's the original person mean, not the centered version. To demonstrate the other way of setting up the model that I'd like less, but which is more common, here's the third way to make a negative mood variable. So we'll skip that for now and pick that up later. And then I have a variable for gender in my data set where men are 0 and women are 1. And so that will be my moderator. So any questions on the setup or the story? All right. So first things first, let's find out if I actually have longitudinal data, both with respect to the predictor and the outcome. And let's see. I have by the way, I had fixed this just a second ago. I realized these still said example 1. That was when I made this first, thinking this would be my first example, and then I decided to add the previous one. So these are from example 2 if you're playing along within the programs. So I'm fitting an empty model. Empty means random intercept model for my glucose in the AM, which has been log transformed because it had a very long tail to try and reel that in. This is to see how much of its variation is between persons versus within persons. So here are the estimates. UN11 is my random intercept variance. That's level 2. Day, then, is level 1. So I can make an interclass correlation as level 2 over level 2 plus level 1. And that works out to be an interclass correlation of 0.69. So 0.69 is the percent that is between or within, folks. Between level 2 or 1. 2, cross-sectional or longitudinal? Cross-sectional, very good. So 70% of the variance would have been there had I measured these folks once. 70% is because some people have higher glucose in the morning than other people. So 31% has something to do with time. Negative mood, then. Same idea. Even though I'm thinking of it as a predictor, it's a time-varying variable that I can partition its variance the same way as I did for glucose. So I'm sticking it in an empty model. Comparable figures, then. This leads me to an interclass correlation of 0.39. Nope, this is just description. But yes, this is foreshadowing that I could do this instead of using the brute force if I switch software packages. Yes. So 39% between. So I have some between variance. That means to the extent that some people are grumpier than others, that's 39% of this variance. That can predict why some people have higher glucose than others. The remaining, let's go, 61% that's within in this variable can predict why some people's glucose is higher on certain days than others. So yes, now comes the brute force. So I use the term brute force to convey the idea that we are carving up negative mood into approximations of its level 2 versus level 1 variance. So here are the two effects that are going in the model. At level 1, I have a beta 1 placeholder, and then I'm showing that I'm doing person mean centering here by saying it's mood TI, so time varying mood, minus the mean of mood for each person, so the mean for mood I. So that conveys the idea that this is within person variance and mood only, and I'm giving it a fixed effect only for right now. I'm also simultaneously adding at level 2 person mean mood, not centered since it's 0 already means something, and giving it a fixed effect. So I'm entering at level 1, within person negative mood is my predictor, and at level 2, person mean negative mood as my predictor. Random intercept only in terms of my model for the variance. See, and you'll notice I figured we'd be tired by now, so I just wrote out the answers for you. So in my regular class, I'm not that nice. So we can go through some of the estimates here. So the fixed effects are what's of interest right at the moment. So my intercept, 4.9 is the average log glucose score, and that is conditional on when the predictors are 0. So in this story, it's not time 0, because time's not in the model, but it is conditional on person mean negative mood equals 0, so this is someone who's at sample average levels of grumpiness, and conditional on within person negative mood equals 0, which is when someone's having an average day. So you can think of this as the expected log glucose for an average person on an average day. From there, both of these effects are significant. I do want to point out, though, the sizable differences in their standard errors as well as their degrees of freedom. There's a lot more information within persons than between persons in these data. I've got 21 days per person, so that's a lot more. So a lot smaller standard error. Degrees of freedom is huge. So first off here, within person negative mood, that's my level 1 effect. So for every 1 unit increase in negative mood relative to my own average, so when I am grumpier than usual, for every 1 unit grumpier I am, my glucose that same day, so it's on the same row, goes up by 0.01. So at this point, when you're writing these types of results, you have to be very careful to differentiate what the effect means at each level, otherwise it gets confusing, because negative mood has 2 different predictors in this model. So this one is specifically the effect of more negative mood than usual on that occasion's outcome. So it's an acute effect, essentially. The other one, this is my level 2 between person effect. For every unit grumpier I am than other people, so for every unit increase in person mean negative mood, my overall glucose average goes up by 0.08. So this is more of a state, whereas within person is more of a trait, or you can think of between person as a chronic versus an acute. So the person mean lifts the entire trajectory up, whereas within person, it's only at that day, because it's a within person fluctuation relative to your usual level. In terms of effect size, then, we've got 2 fixed effects and 2 piles of variance. Which goes with which? And I know it's like 3:30 on a Monday, but we can handle this one, right? So if I were going to pick which one for within person negative mood, is that level 1 or 2? 1. So which one of these is level 1 and which one of these is level 2? Day is level 1. We have a winner. So to the extent that being grumpier than usual matters, that would have reduced my day level residual variance at level 1. And to the extent that being a grumpier person matters, that would have reduced my random intercept variance at level 2. And yes, in the paper, we actually wrote grumpier person and grumpier day. And reviewer 3. Quite possibly. They didn't appreciate the informal language. Well, I don't appreciate it when people make things sound harder than they need to. And grumpy person on grumpy day makes it a little bit easier.
Did you respond back to you're a grumpy person?
No, we apologize that our tone was not perceived well. Yeah. So this is why I liked setting this up this way. You know what the variable means. You know what it should do. You can put them both in at the same time, and they each tackle their own respective level. Ta-da! Right. Was that funny? No? Okay. It's okay. If it was funny, I just want to know why. So pseudo R-squared then to get the actual effect sizes that go with these things. Even though they were statistically significant, it's hard to get too excited about these. A 0.2 reduction in the residual variance and 3.3% of the random intercept variance. That's what we got. So not nearly as exciting. If I do a total R-square, so if I just want to know how much variance did negative mood account for, put it back together again. I got 3.3% of the intercept, and I got 0.2% of the residual. To be able to interpret those numbers, I have to know what the original interclass correlation was. I believe the interclass correlation for glucose was 0.69. So if we put that together, person mean differences in negative mood at level 2 accounted for 3.3% of the original 69% that was between persons. Within person fluctuation in negative mood accounted for 0.2% of the 31% that was within persons. And at this point, your reader's going, what? And so you do them a solid, and you say total R-square 0.023. So the squared correlation between the outcome predicted by the two halves of negative mood and the original outcome, that's total R-squared. And if you were to do that weighting, 3.3% of the 69% plus 0.2% of the 31%, you'd get something pretty close to this number in balanced data. Since we're in maximum likelihood, we can also do a -2 log likelihood test for the two effects if we wanted to, and so here's an example of how to do that. Okay. So how are we doing so far? This isn't so bad, right? More than others, more than usual. Between, within. Level 2, level 1. Inter, intra. Cross-sectional, longitudinal. Random effects. So the answer is right in front of you, but if you'd like to impress your colleagues on how smart you are, which of my two effects of negative mood could possibly be random? Within or between?
Only lower levels can be random and higher levels.
Yeah, only the lower ones. So a level 1 effect of within-person negative mood can vary randomly over level 2 persons. The level 2 between-person negative mood effect cannot vary because it needs a 3 to vary over. So I'll say that again. The level 1 within-person negative mood effect can vary randomly over level 2 people. The level 2 between-person negative effect does not have a level 3 over which to vary randomly. So does the extent to which being grumpier than usual make you sicker than usual that day, does that vary over people? Survey says. I've added a new random slope variance. So it is individual differences in the extent to which more negative mood than usual means more glucose than usual that day. Adding that random slope variance and its covariance with the random intercept, it's a -2 log likelihood difference. Survey says no. So it looks like people don't need their own within-person mood effect. But if this was my dissertation and my proposal said I was going to examine gender differences, then I'm going to examine gender differences. So this is what it would look like if I wanted to know if between and within-person effects of negative mood differed between men and women. So here's my new equation. Before I jump into this, any questions so far? So gender is coded so that 0 is men and 1 is women. This is a classic binary example. In this case, gender is time invariant, so it goes into my level 2 model. So the level 1 model is the same. Each person gets their own intercept, and each person gets their own within-person negative mood effect. And you'll note, I started this convention a few years ago, and I'm just going to keep doing it. I write out what the betas are for. That's for my own benefit as well as for the readers. This is how each person gets its own intercept. This is how each person gets its own within-person effective negative mood. So then I am adding here gamma O2. It's O because we're predicting beta 0, so everything in this line starts with a 0. This effect for the men versus women is the second predictor of beta 0. The third effect of beta 0, third predictor of beta 0, is a two-way interaction of person mean negative mood with gender. So these two new terms both go in the beta 0 line. They predict intercept differences, so they would reduce U0 random intercept variance at level 2. So this is a level 2 main effect, this is a level 2 main effect, and this is a level 2 interaction between two level 2 predictors. Then down here, note that I've left the hole where another predictor could have gone. That's a convention that I do also to try and illustrate what is and isn't in these models. So I left a hole for it and I left a number for it in case I were to add it later. But what we're saying here is that the within-person effect of negative mood starts with the fixed effect and then how it differs between men and women. So given the coding, this fixed effect within-person negative mood is specifically for dudes, and this is how it varies for chicks. Likewise, this is the person mean effect of negative mood for gentlemen, and this is how it differs for ladies. Which variance term do you think this interaction right here is going to capture? So this is gender by within-person negative mood, gamma 1, 2. Which variance component is that going to capture? There's only two choices. The one that's not in its line, no. The one that's in its line is what I would normally say, but it's not here. We don't have a random slope. We just decided not to keep it because it wasn't significant. So what's it going to do? What's left? Residual, yeah, it's coming out of here. So a cross-level interaction of a level 2 by level 1 predictor can explain residual variance if the level 1 predictor does not have a random slope. Here's my 3 new terms. And here's an example of how I get all of the effects for men, for women, and their differences. Intercept, within person effect, and between. We'll talk about the last one a little bit later. Here are my new fixed effects. So the main effect of gender here, this is the simple main effect, specifically when within and between person negative mood are at 0. That refers to gender differences in level of glucose, of which there are none that are significant. This is my within person negative mood effect, given its interaction with gender. This is specifically for men. So in men, for every unit more grumpy you are than usual, that day's glucose goes up by 0.03. In women, what happens to that within person negative mood effect? Which pattern is this? It becomes 0. Yeah, I would say it's significantly less positive. So it is a positive effect in men. The interaction term gives the difference in the effect for women. It is less positive in women and takes it down to basically 0. So right now the model tells us what it is for men, whether it differs for women. To get what it would be for women, that's what those extra statements that I wrote get you. So there is what it ends up being once you do the math. Likewise, here is my between person negative mood effect. In men, for every unit grumpier you are than other men, your glucose goes up overall across all the days by 0.2. What does the interaction term with gender do to that one? No one wants to be brave. Same, yeah. Less positive. Significantly less positive in women. So there's all of the effects that the model predicts. You can ask for the ones that are not directly given. The ones that it gives you are the effects for men and the differences between men and women. The ones for women are the ones that are implied. And here's a picture. Yeah. We haven't talked about that yet. Yeah, so I don't need to remind you because you haven't forgotten. But we will, we'll get there next. So here is the type of picture that I would make to display these kinds of effects, where the x-axis is not time, but it is actually within person variation in mood, where I would look at the standard deviation of the within person variable to figure out what representative values of high and low would be, so plus or minus 1 standard deviation. And I have different lines for different between person values, all the predictors. So we have happy man, grumpy man, happy woman, grumpy woman. So So first off, if we look at the individual lines, the slope of the blue lines is the within-person negative mood effect for men. The slope being less positive and flat is the within-person negative mood effect for women. And gender by negative mood is the interaction term that tests the difference in the blue slopes from the red slopes. Then to do the between-person side of the model, that's given by the vertical distance between the lines. So if we look at the distance between the blue lines, that conveys the between-person negative effect for men. The fact that the distance between the blue lines is much bigger than the distance between the red lines conveys the person-mean negative mood by gender interaction. So the red lines are on top of each other. There is basically no between-person negative mood effect in women. It is significantly bigger in men. Within a color, they're parallel because there's no between by within interaction. And there's my pseudo R-square for all that stuff, as well as total R-squared. Oh, and by the way, when this example is all the way done, here's some words, in case you didn't catch all of that. Have some words. Okay. I am using it as a moderator of the within effect and the between effect, yes. Certainly. Absolutely. Another thing I could have done that I didn't was have the between moderate the within. Is the effect of being grumpier than usual dependent on just how grumpy you are? And does that differ by gender? So that would be a three-way interaction. I didn't do that because that was nice. Figured this is enough. Yes, ma'am. In this study, we didn't have any such people. So sex was something that was time invariant. What he was asking about is the role of sex in the model. So we are saying that there can be gender differences in a level 1 effect of mood, as well as gender differences in a level 2 effect of mood at the same time. Not that gender has a level 1 effect. So, not in this study. Other questions? I don't know of any software that would give you an optimal combination. Yes and no. So the question was about strategy in terms of evaluating lots of predictors. I tend to have two different kinds of models. So in a situation where there's a lot of potential predictors that are of interest, what I would do first is look at each predictor in a separate model, but the between and within simultaneously, because those things are uncorrelated. They are not going to fight against each other. You will get the same answer back if they're in or not in within a little bit of decimal places if you have unbalanced data. So then, like for instance, with this, I could say, is negative mood related to glucose? Okay, next, check. Then is positive mood related to glucose? Next, okay, check. And I'd go down my list and see what's related. And then once I know what is or isn't related bivariately, you would then combine them together into whatever combination would address the questions that you have. A lot of questions are phrased as like, after controlling for blah, does this other thing matter that's new? In which case it would dictate a model where they're combined. And so the purpose of executing the individual models first would be to say, well, like positive mood is not related once you put negative mood in the model, for instance. It's not that positive mood wasn't related, it's that it's not related anymore after you control for this other thing. So putting each predictor, each set of predictors, the between and within, in separate models allows you to just assess whether it's related in the first place, and then to evaluate its unique combination with other variables. So the way that they get combined is going to be dictated by a lot of things, and there's not necessarily one recipe for that. But I do believe in having bivariate versions and then combined versions so that you can differentiate unique effects. All right. Other questions? Yes? Yeah, so when I think of the predictor, like if I think of negative mood as one predictor, I'm actually thinking of its two parts going into the model at the same time. I would not put the between in and then the within in a different model because they each have a different job to do. And you've set them up to be orthogonal, so you don't have to worry about them competing against each other. Within person negative mood, its job is to tackle the level 1 residual variance. Person mean negative mood, its job is to tackle the level 2 random intercept variance. And so its total contribution really needs both of them in there to the extent that that predictor has variance at each level. All right, other questions? Now let me answer the other one. What's a contextual effect? Because that's the other piece here that you might want to know, although it doesn't make as much sense in longitudinal data, but that's what the other method of centering is going to tell you. So this is the missing piece here, a contextual effect. You can think of this two different ways. One of them is a more statty way, and the other is a more interpretive way. The definition of a contextual effect is the difference of the within from the between effects. It's the difference between the two. So an easy way to explain it, let me go back to the model without gender in it to demonstrate. I have my within effect at level 1. I have my between effect at level 2. If I want to know if those coefficients are significantly different from each other, I ask the software to subtract them. So when I say person mean has a coefficient of 1 and within person it's a negative 1, that's the same thing as asking it to do a subtraction. Then when we get to the results here, I labeled each of the effects so that they would be easier to track, but you can see that the within person effect that's given by the model is right here. The between person effect at level 2 that's given by the model is right here. And the difference between this 0.08 and this 0.01 is this 0.07. So to me, that's the easiest way to understand what a contextual effect is. It's literally the test of whether the between effect differs from the within effect. And in this example, 0.08 is not the same as 0.01 because of this p-value. Now, while that is easy to understand, you might be thinking, why the hell would I ever want to know that? That doesn't really lend itself to hypothesis testing. But it does when you phrase it as what the other way of thinking about a contextual effect. To try and explain it that way, I have to make up a new word. The new word I will be making up is extrapolable. So if I have a daily diary study, and every day I ask you for a mood reading, and today you're like, I'm grumpy, and the next day you're like, I'm still grumpy, and the next day, I'm really grumpy now, one might infer that perhaps you are a grumpy person. So to the extent that you behave in a consistent way across days, your grumpiness on any one day, you can somewhat extrapolate what kind of person you are. So then the question is there anything to be added by considering what happens on those other days to describe the sum total of your experience? So the other way to think about a contextual effect is that it represents the incremental effect of the person mean that is not extrapolable from their daily observation at level 1. So this 0.01 within person effect, it could actually be the same thing as a between person effect. If there was no extra influence after controlling for today's negative mood, if being a grumpy person had nothing to do with anything, then there is no extra contribution. This contextual effect for that extra contribution would be 0. The contextual effect is the extra effect of level 2 above and beyond controlling for the absolute value of level 1. So once I know whether or not you're having a grumpy day, does it matter what you said the rest of the days? If it does, we have a contextual effect. So within plus contextual equals between. So between person, as labeled here, and contextual are both level 2 effects. Between person is not controlling for today. Contextual is after controlling for today. In longitudinal data, occasions are not separate entities. And so it's weird to me to think about controlling for today's score. This idea of a contextual effect of the extra effect of level 2 after controlling for level 1 makes way more sense in clustered data. So if I have clustered data, let's talk about students in schools, for instance. And a whole host of literature would suggest that higher SES kids have better academic achievement. Okay? So if I want to look at the relationship between individual SES and academic achievement, I can put in child SES as a predictor in the model. But to the extent that rich kids go to better schools, the effect of SES is also a school effect. So to be able to approximate that, what I'd want to do is calculate the mean SES of the kids in a school, and that goes in the model at level 2. If I use grand mean centering at level 1, which is the alternative version of this that directly gives contextual effects, what I end up with is the individual child effect of SES and the contextual effect at level 2 that says after controlling for individual child SES, what is the extra bonus of going to a rich school? After controlling for the level 1, what is the incremental effect of the level 2? That's what the contextual effect means. It makes more sense in designs in which the level 1 units are separate entities. In longitudinal data, an occasion is not really a separate thing, the way a person is a separate thing in the context of groups data. Fortunately, any one model can give you either of these, between or contextual. This version gives you within and between. The other way of setting up the level 1 predictor gives you contextual instead. So this is the other way of people specifying time-varying predictors and the way that it is much more easy to screw up grand mean centering at level 1. So the switch, the level 1 predictor, is centered at a constant rather than a variable, and that is going to wreak havoc on our model. The reason goes back to regular old regression. So if I put x1 and x2 into the same model, their slopes are going to be different than if each one is in the model by itself. To the extent that they're correlated, their slopes become their unique effect after controlling for the other predictor. Keep that idea in your head, and we'll look at what happens in this context. So either way, we're putting the same level 2 information in the model. So here's 2 rows of data for one person, here's 2 rows of data for another. This person has a value of 2 and 4, this person has a value of 6 and 8. So for the first person, their person mean is 3, the second person, their person mean is 7. I want to center that at some middle value, let's pick 5. Here's the level 2 variable that goes in the model. The person mean centered at a constant so that 0 means something. So this person is low on average, this person is high on average. Now the 2 choices for what goes in at level 1 are over here. What we just did is person mean centering. We take the original time varying predictor, we remove the level 2 person mean variance from it. So all that's left is relative information. We know that at this occasion this person was relatively low and they were relatively high. The other person was relatively low and relatively high too. It's purely level 1 information here. So this is purely level 1. It has a purely level 1 effect. This is purely level 2. This has a purely level 2 effect. They don't fight against each other. Now watch what happens though if we swap out within person X here for this original time varying X, perhaps centered, that doesn't really matter. Now it still has both kinds of variance in it. We've just shifted it over on the x-axis. We haven't done anything to decompose its variance. So it has level 1 and level 2. And when you put that into the same model with another level 2 variable, they're going to fight against each other. So here's what not to do. This is the number 1 multi-level modeling thing done wrong. This is smushing. So this is time varying X that has both level 1 and level 2 variation in it. I put it in my level 1 model because I'm thinking of it as a time varying predictor, and I don't do anything at level 2. So I've only given it 1 coefficient to do the work of 2 different variables. So that 1 coefficient is what I call the smushed effect. It's the between effect and the within effect smushed together. Otherwise known as a convergence effect, a conflated effect, or a composite effect. I like conflated the best of the synonyms because I think that also gets at this idea of smushed. It's going to be more heavily weighted towards the within effect because there's more information, more sample size at the level 1. But what you're doing here in putting 1 effect in is that you are saying that the between effect and the within effect have to be the same number. They're equal. So you can get by with 1 coefficient to do the job of 2. So this is what not to do. So graphically, this is what just happened. We're taking this X that has 2 kinds of variance in it. We're not differentiating its kinds of variance. And so we're saying that each type of variance, level 2 green here and level 1 purple, has the same effect. They both have that same fixed effect between and within. Here's how we fix it. We introduce the person mean at level 2. So this is slide 22 here. So in the language of regression and unique effects, time varying X has both level 1 within and level 2 between. Person mean X has only level 2 between. So what is the unique part of time varying X going to be? Say it again. Time varying X still has both level 1 within variation and level 2 between variation in it. Person mean X has only level 2 between variation. So when you put these two in the same model and they fight against each other, what is unique about time varying X? What's its unique effect going to represent? We end up back at the same place that we were in person mean centering, but not because we brute force made the variables work that way, but because statistical control turned it around for us. Yep, this is an equivalent model to person mean centering at this point, just rearranged parameters. The within effect at level 1 is exactly the same that you would get in using person mean centering instead. But it's because you've uniqueified time varying X. There's another word for you. We have uniqueified time varying X by controlling it for person mean X. Its unique variance, it's within. Person mean X has only level 2 variance, and so you're thinking, well, that should be the level 2 between effect, right? That's nope. It's contextual. Because it also has to be uniqueified relative to the other predictor. So I have a picture that might help. Here's what we've done. So we started off with all of the variance here in time varying X, level 1 and level 2, and we gave it one effect that was supposed to do the job of both, the smushed effect. We then added a level 2 person mean covariate that picks up the remainder of what it should have to get to the full level 2 effect. So the part that was extrapolable from the day is down here, and the person mean variable picks up the extra. It picks up the contextual incremental effect of the person mean after controlling for the absolute value of the level 1 predictor. But within plus contextual equals between. Between minus within equals contextual. You can get back and forth. Here's a picture. So this is on the x-axis time varying stress. The slope through the person means is still the between person effect. The slope of the individual lines is still the within person effect. But now the slope, if you can say that for a vertical line, is given by this line right here. This is the contextual effect. So if we control level 1 for the same value, say condition on 5, after controlling for how much stress you have today, what is the extra effect of being a stressed out person? What is the shift in the intercept straight up at the same level of X that is caused by these differences in person means? That's contextual. So contextual is this black line. Between is the yellow line. Within are the separate lines. Math. For those of you who don't believe me, math. Same thing with interactions. You can't smush those either. All right. So that's the contextual effect. Let me go back to our example real quick to show you what happens. So let's start with the grand mean centered version. Part 3, picking up on page 10. first model what not to do. First model puts time-varying negative moon in the model all alone. Thinking, well, it's a level 1 predictor, I'll put it in the model. The coefficient you get back is pretty much the within effect. The reason that this is wrong is because this model has only one effect to do the job of 2. It says the within effect is 0.01 and the between effect is 0.01. But we already know the between effect in this example is 0.08. So it's the level 2 model that suffers when you smush things, not the level 1 model. So when you're reading people's papers or tutorials, there are 2 dead giveaways that you can tell when someone has smushed something, and therefore you should be skeptical of whatever they're telling you. Number 1 is when you see a table of results in which the same variable is not mentioned both at level 2 and level 1. So if you get a table of results where you have something like time-varying negative mood, and there's nothing in the table about person negative mood or person mean negative mood or something that would convey level 2-ness, it's smushed. Here's the other way. When people tell you that a level 1 predictor explained level 2 variance, that cannot happen. So here's what happens when we fit this smushed model. We get the 0.2 of the residual that we got from the correct version of the model. The within model is fine. But we were supposed to have gotten 3.3% of the random intercept. Instead, I only got 0.9%. That's because the correct between effect is 0.08. 0.08 should have explained 3% of the random intercept variance. This model says the effect is 0.01 instead of 0.08, and it's not big enough. So it didn't capture as much random intercept variance as it should have. And so this is how you can tell that there was smushing at all. If you have a predictor that is purely level 1, random intercept variance should go up, not down. Whenever you explain residual variance at level 1, the random intercept variance increases. If you have level 2 random intercept variance that decreases because of a level 1 predictor, it is smushed. Because the only way that a level 1 predictor can account for level 2 variance is because of the level 2 variance that is hidden inside the level 1 predictor. That is what reduced the level 2 random intercept variance. Does that make sense? Or have we hit the wall? Yeah, I hear you. We'll review this tomorrow. How's that sound? Does that sound fair? But here's how you fix it. Just put the person mean in. If you want to use grand mean centering at level 1, fine. But the person mean then that gives you the contextual effect. So after you put the person mean in, there's my 0.07 that picks up the difference. And adding that person mean contextual effect brought my total R square up, or excuse me, my pseudo R square for the random intercept up another 2 point whatever percent and got it back up to where it's supposed to be. So you might be wondering, if I have this preferred way of doing things, a person mean centering, and that way makes more sense, why am I belaboring this? Do you know why? Because M+. Because what's going to happen is that we're going to set up a model one way, and it's going to be a between effect. And we're going to set up the exact same model using a different version of their syntax, and it's going to switch to contextual. And then we're going to set it up a third way, And some of the effects are contextual, and some of them are between. So because between and contextual are two different versions of a level 2 effect, you have to know what they mean, and you have to know what your software is giving you. So this is where the interface of model and software gets very tricky. I would love it if everything were between instead of contextual, but that's not always possible. So that's what we get to tackle tomorrow. So you will note the linear combinations of predictors here that are not given by the model. So this version of the model gives you within and contextual, but within plus contextual gets you back to between. So level 1 within plus level 2 contextual equals level 2 between. Level 2 between minus level 1 within equals level 2 contextual. You can get from one to the other. Let's see if I can say it correctly. Level 1 within plus level 2 contextual equals level 2 between. Level 2 between minus level 1 within equals level 2 contextual. They are identical models so long as the level 1 effect is fixed. Once the level 1 effect is made random, they are not identical models anymore. You cannot make the random effects equivalent. Then you have to pick which way it should go. There's a little bit of research saying that person mean centering is better than that. You could always do AIC and BIC to see which version you prefer. Words. So you can see the way that I tried to talk about these things, lumping the effects together across models. So I present the within effects, the between effects, and the contextual effects. So let's play reviewer 3 for a moment here. Reviewer 3 doesn't understand why you have two different versions of mood in your model. I don't think that you can do that because collinearity and stuff. What's your response? I'll start you off. Dear Reviewer 3, we apologize that we were not sufficiently clear in explaining our model specification. Because when someone gets it wrong, it is your fault, not theirs. Now that you've apologized and eaten your humble pie, how do you respond? What do you think?
Please take this course, Dr. Hoffman.
Yeah, nope. Reviewer 3 is an eminent scientist in his or her field, and they do not have time to retool. But they're standing between you and tenure. What do you do? You partition the variability into within and between, yes. And how did you know that you needed to do that? ICCs. And if you're doing person mean centering, do you need to worry about collinearity? Nope. If you're doing grand mean centering, do you need to worry about collinearity? In the sense that the model effects change once one is in and one is not. So, let me do one last thing here because I think it might help sort of cement things in. 1 second.